Today we're diving into one of the biggest paradoxes in all of mathematics. We're talking about imaginary numbers. For centuries, they were dismissed as this weird mathematical fantasy. But it turns out they are the invisible engine powering pretty much our entire modern world.
And that's the big question, right? It sounds completely backward. How can something we literally call imaginary be a critical ingredient in all the real, tangible tech we use every single day? It seems impossible, but the answer, well, it reveals this incredibly deep and, frankly, kind of spooky connection between abstract math and physical reality.
So, what even is a complex number? At its heart, it's pretty simple. It's got two parts. First, you've got the real part, A, which is any number you're already familiar with. Then you have the imaginary part, B, which gets multiplied by the famous letter I, the square root of -1. You know, when Girolamo Cardano first bumped into these back in the 16th century trying to solve equations, everyone just thought they were fictitious, a clever trick, and nothing more.
But here's where the magic really happens. See, a normal, real number can only show you one thing, a single point on a line. But a complex number, it's a point on a two-dimensional map. And this means a single complex number can hold two totally distinct pieces of information at the same time. Its magnitude, which is just its distance from the center, and its direction or angle. This two-in-one property, that is its superpower.
So, where does that superpower first show up in the real world? Well, it turns out complex numbers are the perfect language for describing anything that oscillates, anything that moves in waves. Think about it. Before this, if you were an engineer trying to describe something like alternating current or a radio signal, you were stuck using sines and cosines. And anyone who's survived a trigonometry class knows that means you're wrestling with this absolute jungle of complicated formulas and identities. It's a mess, it's slow, and it's just a mathematical nightmare.
And this slide just shows you the night and day difference. On the left, you've got that trig headache. But on the right, you have the solution, complex exponentials. Thanks to this beautiful thing called Euler's formula, which connects exponents, sines, and cosines all using the number I, that whole mess just collapses into one single elegant expression. And suddenly, all the hard calculus becomes ridiculously easy. It's the ultimate mathematical cheat code.
And this is a great way to visualize why it works so well. We can take an entire wave and represent it as a single spinning arrow called a phasor on that complex map. And as that phasor spins around, its shadow or its projection on that horizontal real axis perfectly draws the exact sine wave we're trying to describe. It's just so elegant, and it's the reason complex numbers are the absolute bedrock for analyzing waves.
And let's be clear, this is not just some abstract math problem. This shorthand is literally running our world. It's how engineers analyze the AC power grid. It's the math that filters the static out of your phone calls. It's transmitting the data that makes crisp images appear on this very screen. And it's even used to model the gigantic waves in our oceans and atmosphere for weather forecasts. But their power doesn't stop with 2D waves. That's just the beginning. What happens when we need to move from a flat map to rotating things in 3D space? Well, complex numbers have an answer for that, too.
Okay, check out this neat little geometry puzzle. What's the sum of those three angles, alpha, beta, and gamma? Now, you could break out the trigonometry and it would be a huge pain. Or you can use complex numbers and it becomes beautiful. You just treat each of those points as a complex number and multiply them together. Because here's the secret. When you multiply complex numbers, you add their angles. The result is 10i, which is a number that sits straight up on the imaginary axis, an angle of exactly 90 degrees. Just like that, puzzle solved.
Now, that little rotation trick has massive real-world consequences. In fields like 3D graphics and aerospace, there's this infamous problem called gimbal lock. It's this bizarre glitch where a rotating object can suddenly lose one of its axes of freedom. In a video game, that means jerky, weird animations. But in aerospace, it could mean catastrophic navigation errors. The Apollo 11 crew even ran into an issue with it on their way to the moon.
The solution came from pushing complex numbers one step further, and the story behind it is legendary. In 1843, the Irish mathematician William Rowan Hamilton had been obsessed with this problem for over a decade. Then one day, while walking along a canal in Dublin, the solution hit him in a sudden flash of genius. He was so afraid he'd forget it, he famously carved the core formula for a brand new, four-dimensional number system right into the stone of the Broom Bridge. And what he had invented were quaternions. You can think of them as complex numbers on steroids. Instead of just one imaginary unit, I, they have three, I, j, and k. And this four-dimensional system provides this incredibly robust, elegant way to describe rotation in 3D space that completely avoids gimbal lock. It's why they are absolutely essential for pretty much all modern 3D graphics and aeronautics today.
So, up to this point, we've seen complex numbers as this incredibly clever, powerful tool that humans invented. But here's where the story takes a truly mind-bending turn. What if they aren't just a tool we invented? What if they're actually woven into the fabric of reality itself?
This is the question that has haunted physicists for a century. Are complex numbers just a convenient trick that makes our equations prettier, or does the universe, at its most fundamental quantum level, actually run on them? Is I as real as gravity?
Well, recently, a group of scientists decided to stop arguing and finally put it to the test. And the stakes couldn't have been higher. As one of the researchers put it, the experiment was designed to either prove or completely refute a version of quantum mechanics that was built using only real numbers.
So they set up this thing called the Bell game, and it was basically a showdown. In one corner, you had standard quantum theory with all its complex numbers, and in the other, a hypothetical version stripped down to use only real numbers. The rules of the game were cleverly designed so that the two theories would predict different outcomes, different scores. And to make sure the results were rock solid, two separate teams ran the experiment on totally different hardware, one using light particles and the other using superconducting quantum computers.
So what happened? Who won? Well, the standard complex number version of quantum mechanics didn't just win, it wasn't even close. It obliterated the real number version by an absolutely staggering 43 standard deviations. Now, to put that number into perspective for you, in particle physics, a result of 5 standard deviations is considered the gold standard for a world-changing discovery. 43 it's basically unheard of. It is as close to a certainty as science gets, and the implication is just profound. Complex numbers are not just a convenient tool. They appear to be a non-negotiable, fundamental feature of how our universe actually works.
So let's just step back and put this all together. We've watched these numbers go on a journey from a mathematical oddity to, well, the very engine driving our reality. I mean, just look at this journey. In the 1500s, they're a fictitious trick. By the 1800s, they're a geometric tool that gets supercharged into quaternions. Then in the 20th century, they become the indispensable backbone of our entire technological world. And now, here in the 21st, we have actual experimental proof that they are a fundamental part of reality's source code. It's incredible. So, the next time you use your computer, or get a GPS signal on your phone, or see a medical MRI scan, remember that hidden engine. The transistors, the satellites, the medical scanners, the robots building our cars, the very aerodynamic design of the planes we fly in. They all depend on the strange, powerful, and very, very real logic of complex numbers. And that leaves us with one last huge question to chew on. The numbers we humans decided to call imaginary turned out to be more real than anyone ever dreamed possible. So what other strange mathematical ideas are out there just waiting for us to realize that they're not fictions at all, but another chapter in the universe's blueprint?